Math 1314, Section IC1, Spring 2022, Tyler Junior College, Section 7.2, Polynomial Functions, Video 1, Characteristics of Graphs of Polynomial Functions. Before we get into the general discussion of polynomial functions, I want to point out that we've actually already discussed some of these, some very specific types of polynomial functions. So far, we've studied two types of polynomial functions and their graphs. The first type we've studied have been linear functions, functions of the form f of x equals mx plus b, also known as y equals mx plus b. And what do we know about these graphs? Well, we know that these graphs are lines. I'm getting my typing ready to set up. We know the graph is a line. And if you're in the form mx plus b, we know the slope is m and the y-intercept is the point 0, comma b. So there's a lot of information we can extract from about the graph of this function from the function itself. And the other type of polynomial function that we've studied so far have been quadratic functions. That's what the last section was over. Functions equivalent to f of x equals ax squared plus bx plus c. And we know some things about the graph of this. For example, we know the graph is a parabola. It's that U shape. Looks a little something like this. Or it might be upside down if the a is negative. But we can figure out more than that. We know where the vertex is. We know the vertex of this graph is at negative b over 2a, and then the value of the function when we put the value of negative b over 2a inside of it. And again, this is from the previous series of videos, so hopefully that's a little bit current. So there's a lot of things that we know. Now, you may be asking, what makes these polynomial functions, or what are the types of polynomial functions are there besides these? Well, these functions as polynomial functions can be categorized based on something called the degree. I'm going to go ahead and introduce the concept of the degree of a function, of a polynomial function, so that we can discuss it right now. But the degree of a polynomial, or polynomial function, if you will, is, simply put, the highest power of the variable. So in this case, let's see if I can get all this on one line. Maybe I can, maybe I can't. Oh, there we go. The degree of a polynomial function is the highest power of the variable. So for example, for linear functions, the degree is 1 because the highest power on the x is 1. What is the degree of a quadratic function? Well, it's the highest power on the variable, so the degree is 2. And so we started with the lowest possible degree. That wasn't 0. Degree is 1, linear functions. And then we went up to degree 2. And it's natural to think that the next thing we would study are degree 3 polynomials whose highest power is x to the 3rd. Analyze them into oblivion and then move it up to degree 4 and degree 5. But we're not going to do that. What we're going to do instead is talk about the rest of them collectively. In other words, what happens if our degree is 3 or higher? Now, the things that I'm going to tell you are true for when the degree is 2 and when for the degree is 1. But once you go beyond quadratic and get to 3rd degree, it's better to talk about polynomial functions collectively instead of isolate them based on their degrees. All right, so I guess we should start by defining what exactly I mean by a polynomial function, and it would help if I would spell polynomial correctly. In general, a polynomial function is a function equivalent to the following. Now, the trick to defining a polynomial function, as opposed to a linear function or a quadratic function, is we don't know what degree we're dealing with. For linear, we know we start with degree 1, so our first term is an x term. For quadratic, the degree is 2, so our first term is an x squared term. But for a polynomial function, there's no specific degree it has to start with. So how do we represent starting with some degree when we don't know what it is? Well, the same way we represent anything in math that we don't know what it is, we represent it with a variable. The typical variable for the degree of a polynomial that you don't know is n. So we'll say that this is an nth degree polynomial. Let's go ahead and type that here. This is an nth degree polynomial. Just a generic way to represent some degree. All right. Now, so we'll assume this is our highest power. Well, that power of x probably has a number in front of it, so we need to represent it generically. Now, back here, for linear functions, we use m and b specifically because of slope and intercept. But for quadratic functions, we generically used a, b, and c just to represent three numbers that we don't know. So that seems natural to just start with a and then go through the alphabet. But there's a problem with doing that here. We don't know how many terms we're going to have. And in theory, this could have more than 26 letters, more than 26 terms, which means we would run out of variables to use to represent the coefficients, the number in front of the x's. So how can we accommodate that? Well, the answer is we're going to start with a, but not just any old a. We're going to put a subscript on it. Let me write that a little bit differently. We're going to put a subscript that matches the exponent on the x. So we'll say an, meaning the coefficient of x to the nth power. So how would we represent the next term? Well, normally when you write a polynomial, it's from highest power to lowest power. So it goes in descending order of power. Well, if the first power, the highest power, is x to the n, then the next power would be 1 less than that. And we can represent that by saying x to the n minus 1. And again, all I'm saying right here is that this power is 1 less than that one. For example, if n was 5, 5 minus 1 would be 4. That would be the next power. So it's just a generic way to say the next number smaller than that one. Now, what are we going to call the coefficient? Well, we're still going to use an a, but we're going to stick with the convention of subscripting it with the number that matches the exponent. And again, don't get thrown off by the fact that it says n minus 1. All it means is whatever number is here is the same number that we put there. And then we can continue this until we get to the end. Now, how does it end? Well, let's take it to the second to last term, the third to last term, to the x squared term. Well, then we would generically call its coefficient a2. And then the first power term, whose coefficient we would call a1. And then the constant term we could call a0. So it's just a generic way to represent highest power on down. For example, we could say something like g of x, because the name of the function is irrelevant, is we'll say negative x to the 4th power plus 7x to the 3rd power minus 5x to the 2nd power. And let's skip the x term and go plus 7. And if I wanted to identify the coefficients being the numbers in front of the powers of x, we could say that the coefficient of x to the 4th by saying a4 is equal to -1. That's the number in front of x to the 4th, the one being implied after the negative. The coefficient of x to the 3rd would be a3 equals 7. The coefficient of x to the 2nd, a2, would be -5. The coefficient of x to the 1st would be, there is no x to the 1st power because its coefficient is 0. And then the constant term, or the number with 0 x's on it, hence a0, is 7. So that's all this is saying at a generic level. It's pretty easy to spot a polynomial function specifically. Oh, look, it's a polynomial function. It's the sum and difference of powers of x's written from highest to lowest. It doesn't have to be written from highest to lowest, but it typically is. It's just the generic representation that messes with some people's minds because we're trying to generically represent the highest power and all the coefficients in front of the x's. All right, so now that we've kind of defined what we mean by a polynomial function, basically a function equal to a sum or difference of whole number powers of x's, let's talk about what these graphs have in common, because they look real different, but they all have something in common. 1 second, I got to fix a typo. All right, although the graphs of polynomial functions vary greatly, there are some features they all have in common. The first one is the graph of a polynomial function is continuous. Now, there is a rigorous definition in calculus for the word continuous, but for our purposes, continuous basically means unbroken, which has an R in there somewhere. So for example, if I were to draw a graph that looks like this, that is continuous. It's unbroken. However, if I were to draw a graph that looks like this, let's move this graph over underneath the word continuous, just so it makes sense to put it there. But if I were to have a graph that looks like this, let's see, it starts out low and it kind of goes up, and then there's this break, which I'm going to represent with this dotted line. And then down here, we have another piece that looks like that. That is not continuous. And the word for that is discontinuous. And if you gave me the X value where it was broken, for example, if this were 2, then we could say it's discontinuous at X equals 2. And there are functions that do this. I'm going to demonstrate them in a website called desmos.com. I think I might have shared this website with you before, desmos.com. It's a free online graphing calculator, a free online scientific calculator. If you click here, there's a lot of things that it can do, but it's really good as an online graphing calculator. For example, if I were to graph f of x equals x to the third power minus 2x squared plus 1, you'll notice that this graph is continuous. It's not broken anywhere from left to right. It just keeps going. Now it's got some special dots highlighted, and I'm not too terribly worried about those right now. But this graph is not broken anywhere. It's continuous all the way around. Now, by contrast, if I had something like this, g of x equals, we'll set up a fraction. On the top, we'll put x plus 1, and on the bottom, we'll put x minus 2. Notice that this graph is broken. I'm going to throw a negative in front of it just because I want it to look like the graph that I drew a minute ago. This graph is broken because the left half of it goes up, and it keeps going up, and it keeps going up, and it's getting more and more vertical, but at no point does it ever connect with the graph on the bottom. And you can see this by simply zooming out and see that there are actually 2 branches of this graph, the one on the left and the one on the right, and they seem to be broken. Oops, wrong way. They seem to be broken at x equals 2. I can check that by typing x equals 2. It will draw a vertical line, and we'll see that we get closer and closer to that line on the left, closer and closer to that line on the right, but at no point does it ever cross this. This is actually a discussion we'll have in the future section about rational functions, but I wanted to illustrate an example of a graph that's broken. I also want to do something else real quick. I want to put this on thicker display mode, and I want to turn off these extra lines so that now we can just focus on the graph. And now we see the broken parts of the graph. The part on the left, well, it's got 2 continuous pieces, but it is disconnected, if you will. All right, so that's what it means for a graph to be continuous. It's not broken. There are other versions of a graph being broken besides having 2 parts separated by a line, but this one will suffice for our discussion. All right, the second characteristic, let's move my picture out of the way. The second characteristic that all polynomial functions graphs have in common is the graph of a polynomial function is smooth. Now, what do I mean by smooth? Well, to show you what I mean by smooth, let me show you the graph of something that is not smooth. We've dealt with absolute value a lot. Let's take a look at what its function looks like, what the graph of its function looks like. If I can get it over to Desmos. There we go. Let's clear all this out. And I'm going to type f of x equals, I'm going to open up this keyboard down here, and there's some absolute value bars. And let's just put an x in there, shall we? All right, here's the graph of f of x equals the absolute value of x. This graph is smooth everywhere except at one point. And guess where that point is? Where this graph makes a sharp turn at 0, 0. So smooth means that you're, loosely speaking, smooth means that your graph has no sharp corners. So an example of a graph that is not smooth, this is not smooth because of the corner. We'll draw it real quick to have it saved inside of the PDF of this video. If we had f of x equals the absolute value of x, we would have this V shape that looks a little something like this. But it's not smooth. It's not smooth because it has a corner there, as opposed to something like f of x equals, let's say we have x plus 2, hold on. Let's say we have x times, well, let's say x cubed minus 4x. By the end of this series of videos, you'll know how to graph this, but I'll tell you right now that the graph of this kind of looks like this. And that is smooth. Smooth because there are no corners. There's a more rigorous definition of what it means to be smooth, but it involves calculus. All right, so graphs of polynomial functions are continuous, meaning they're not broken, and they're smooth, meaning they have no corners. And there is one more feature of polynomial graphs functions I want to share with you, and it has to do with the degree of the graph. If the degree of a polynomial function is n, in other words, if the highest power is n, then, well, I want to kind of get you to see it. I'm going to type a really lengthy polynomial function. I may have to zoom out to see some of it. We'll say f of x equals x to the 4th power minus 3x to the 3rd power plus 17x to the 2nd power minus 54x plus 11. Now, I've gone so far out of whack that we can't even see the whole graph. All right, this doesn't do what I wanted to do, so we're just going to clear this out and make another one. There's a point that I'm trying to make, and trust me, I know exactly what I want. I want x to the 4th power. We'll go minus 13x to the 2nd power and plus 36. And I'm going to do one more thing to this function. I'm going to shrink it a lot. I can shrink it a lot by multiplying by a small number in front of this. So let's multiply this by 0.3. That didn't shrink a whole lot. How about 0.1? There we go. All right, so this is the kind of graph I wanted to see. All right, so this is a 4th degree polynomial. I've got a 0.1 factored out of it. I could redistribute it if I wanted to. But what do you notice about this graph in terms of how many times it turns? Well, it turns when it hits the bottom here. So there's one turning point. Turns when it hits the top, then it turns when it hits the bottom again. This is a 2nd turning point. So this graph has 3 turning points. This 4th degree polynomial functions graph has 3 turning points. What if I had something like this? F of x equals, we'll say x to the 5th. It's really hard to make these that turn the maximum number of times. Minus x to the 4th. Oh, what happened there? Minus x to the 4th plus 4x to the 3rd. Let's do a minus 2 here. I'm trying to get this to really curve a lot. It's kind of hard to make this do what you, well, you know what? I'm going to cheat. What I'm about to type is a 5th degree polynomial function. It may not be obvious from the beginning. I'll explain why in a second it is. We'll put an x, and then we'll put an x plus 3, and then we'll put an x plus 1 in parentheses, and then we'll put an x minus 1, and then we'll put an x minus 2. All right, so I've got this really messed up function, and I'm going to put a scaling in factor in front of it to shrink how tall it gets. Why don't we put a fraction like 1/5? There we go. All right, so now we got this 5th degree polynomial function. And the way you know it's a 5th degree polynomial function is because there's a total of 1, 2, 3, 4, 5 x's. And if I multiplied it all together, I would get x to the 5th. But my real question is, how many times is this 5th degree polynomial turn? Once at the top, 2, right there, 3, 4, and it turns 4 times. So when it's a 4th degree polynomial function, it turned 3 times. When it was a 5th degree polynomial function, it turned 4 times. We already know some other examples, like a 2nd degree polynomial function. This one's easy to show. F of x equals x squared minus 5x plus 3. That's a 2nd degree polynomial function, and it turns only once. So what does that suggest? Well, it suggests that the degree has something to do with the number of times that it turns. I'm going to go ahead and show you what the statement says, but then show you why it doesn't say it turns exactly that amount of times. If the degree of a polynomial function is n, then the graph can turn at most, emphasis on the phrase at most, n minus 1 times. So for example, come on, type. A third degree polynomial functions graph can turn at most 3 minus 1 is equal to 2 times. It doesn't have to turn 2 times, but it can't turn more than that. A fourth degree, I think there should be a dash there. If not, oh well. A fourth degree polynomial functions graph, a lot of words in here, can turn at most 4 minus 1 is equal to 3 times. So if you know the highest power, subtract 1, and that's the most number of times the graph can turn. I say most, but it doesn't have to turn that many times. I'll show you an example. Let's say I just take f of x equals x to the 5th, and that's it. That's it. How many times does this graph turn in the sense that it changes directions vertically? Goes up, then goes down, or it goes down, then goes up? Well, the part that we can see doesn't change direction at all. It's moving up. It kind of teases. Let me zoom in the middle here. It kind of teases that it's going to turn, but it flattens out, or it looks like it flattens out and then continues going upward. And if we were to zoom out, you would see that that's it. There's no more part of the graph where it turns anywhere. I'm just jumping up in the sky and I'm not seeing any more turns. Similarly, if you had something like f of x equals x to the 4th power, before I type the 4, we expect it to turn at most 3 times, 1 less than the degree. How many times does this graph turn? Well, it's going down and it's going up, so it only seems to turn 1 time. And if you zoom out, you'll see that indeed, you really can't tell I'm zooming out because there's no scaling on this graph. I can set that up real quick. If you give me 1 second. Let's put the grid back in the axis numbers. And now you can watch the numbers on the axis. You can tell now that when we zoom out, 10, 20, it's like we're jumping up in the sky and getting a bird's eye view of the graph, and we don't see it turning anymore except that 1 time at the origin. So this statement about if the degree is n, then the graph can turn at most n minus 1 times, provides what's called an upper bound for the number of times it can turn. It can only turn up to so many times. It can turn less, it just can't turn more. So those are the 3 characteristics you need to know about the graph of a polynomial function. It's continuous. I'm going to highlight the important words. It's continuous. I wanted to square, but I think that will do. It's smooth, meaning no corners, and it can turn at most n minus 1 times. You just have to remember that n is the degree.